We will now discuss importance sampling according to the BRDF. Simple cosine sampling that you've seen already is suitable for Lambertian or near Lambertian BRDFs. However, cosine sampling in itself is not suitable to deal with specular BRDFs. For specular BRDFs, we need to actually importance sample according to the specular component of the BRDF. For now, for the assignment, we'll talk about the modified Phong BRDF and the GGX model, which has recently become very popular in computer graphics. In general, sampling of BRDFs is non-trivial. I'll talk about it a little bit in the last segment of the lecture. You can normalize the BRDF to get the probability distribution function, but sampling is still non-trivial. For now, you sample according to a probability distribution function that is close to the BRDF, may not be exactly the same as the BRDF, but this is okay. This is still better than uniform sampling. And the procedure is always guaranteed to work because for Monte Carlo sampling to be unbiased, you just need the function divided by the probability. First, let's talk about a Phong BRDF. In this case, the BRDF is proportional to cosine power n of some beta angle, which is the angle between the outgoing ray and the ideal mirror direction. Typically, there is a constant scale factor associated, and in this homework assignment also you have that, so it normalizes correctly. You typically cannot sample this thing times cosine theta in. You can only sample the BRDF itself and multiply by cosine theta in. But that's okay because it's still better than uniform random sampling. Here is the standard way in which you can do Phong importance sampling. You generate a z in 0 to 1, that's just your uniform random number generator. Then you let this gamma is equal to the inverse cosine of z to the power 1 over s plus 1. That's inverting the cumulative distribution function. Finally, you let generate phi gamma in the 0 to 2 pi range. That's 2 pi times your uniform random variable. This gives you the direction with respect to the ideal mirror direction, and then you need to apply a rotation or a coordinate frame transformation to actually get the direction. In this case, z will point towards the mirror direction. Let's look at what the assignment is asking you to do in terms of modified Phong sampling. We are going to directly sample the transport function which has the cosine multiplied in. And we are going to pick a simple approximation where the cosine is already divided out and cancelled out so that you have a simple Phong form for the specular BRDF. Notice that we define this value t, which is equal to kd divided by kd plus ks, which essentially gives the fraction of diffuse reflectivity versus specular reflectivity. The overall BRDF will be kd plus ks times the factors of t coming in here. Notice that the BRDF can now be written in this form. You have 1 minus t times the cosine term divided by pi, plus t times s plus 1 by 2 pi times the dot product with respect to the reflected direction raised to the power s. It can be shown that this form actually normalizes out nicely and actually corresponds to a probability distribution function. You can sample it by generating 3 random numbers, xi0, xi1, and xi2 in the 0 to 1 range. Xi0 is used to determine if you are sampling the diffuse lobe or the specular lobe. The diffuse component will be sampled when the value is greater than t, and the specular component will be sampled otherwise. Notice that the factor of t goes with the specular component, hence this is the correct thing to do. The phi will be generated from xi2, and it is in the range of 0 to 2 pi. It is formed by taking a factor of 2 pi and multiplying that by a uniform random variable. Now we come to generate the theta value. This differs depending on whether you're in the diffuse or the specular. If you're in the diffuse, then you do cosine sampling essentially. Theta is equal to the arc cosine of the square root of xi 1. If you are in the specular domain, then theta is equal to the arc cosine of xi 1 power 1 over s plus 1, which is essentially Phong sampling. In both cases, you need to rotate the direction, in the first case corresponding to the coordinate frame associated with the surface normal n, in the specular case corresponding to the coordinate frame associated with the reflected direction r. Remember, r is the reflection of the viewing direction about the surface normal. You then compute the BRDF divided by the probability distribution function. Notice that there is some chance, especially for the specular lobe, that the BRDF sample can be generated below the visible hemisphere. In this case, you simply set the value equal to 0. Here is an image without BRDF importance sampling. You notice that in the near mirror sphere that I've included here in the Cornell box, it's extremely noisy with a few bright spots and most of the regions are black. Whereas if you actually do BRDF importance sampling, in this case with BRDF importance sampling, you see that you are actually getting a nice reflection of the Cornell box. We will now talk about importance sampling the GGX microfacet BRDF model. This is a physically based BRDF model that in modern production rendering has become very popular. So in practice, there are many production renderers that include importance sampling of the GGX model as in your homework. It is physically based and is more accurate than the Phong BRDF model. We will actually discuss general BRDFs in the final segment of this lecture. This is a high-level review. The assignment actually goes into more details in the step-by-step recipe for sampling. I will note the images shown here, which show the variety of different visual effects you can produce with the GGX model with different parameters. The GGX model really refers only to the specular term of the BRDF. So the BRDF is composed of the diffuse term plus the GGX term, which is a function of the incoming and outgoing directions. Now the GGX BRDF is a standard microfacet BRDF model. A similar form is used in the Torrance Sparrow BRDF, which was one of the original microfacet models in computer graphics. It has a Fresnel term, which corresponds to the idea that light that comes in at grazing angles, if you view the surface, you get a brighter specular reflection. It has geometric attenuation factors built in, which corresponds to the fact that, especially towards grazing angles, the microfacets mask and shadow the lighting. And it has a distribution term that depends on the half angle, which is the critical term. If the surface is perfectly smooth, this distribution term is essentially a delta function and you get mirror reflection, but for rough surfaces, it controls the roughness. The normalization is required corresponding to the cosine of the incident direction and the dot product with respect to the viewing direction. This is essentially how much of the surface is visible and how much of the surface is lit. Notice that the BRDF is reciprocal as with physical BRDFs, and interchanging the incoming and outgoing directions will not change it. Furthermore, the GGX model has the specific form for the distribution function. The distribution function depends on the half angle. Just to familiarize yourself with the half angle and to review this material, let's assume you have a surface. Along the surface, there is a particular normal. Now assume you have a particular lighting direction. Let's say this is your lighting direction. And let's say this is your viewing direction. The half angle will be the bisector between the lighting and the viewing, where this angle is equal to this angle, and this is the half angle direction. A critical quantity in these half angle models is the dot product of the angle between the half vector and the normal. That's what is known as the half angle. In importance sampling the probability distribution function, you neglect the Fresnel and geometric terms. Your probability distribution function again involves a combination of the diffuse component and the specular component using this factor t and taking the cosine of the incident direction into account. You can show for the GGX model that the probability distribution function is actually very simple. It just involves this term here, which is the distribution term. You consider n dot h and you divide by this omega n dot h. Finally, as a practical matter, the t value is clamped at a minimum of 0.25 to give some specular samples even for low ks because of Fresnel reflection. Notice that the probability distribution function can really be quite arbitrary. It closely matches the sum of a diffuse and specular BRDF, but at the end of the day you will simply divide by it, and therefore slight deviations do not really significantly impact the final result. The recipe for importance sampling the GGX model is similar to what you did for the Phong model. You generate 3 random numbers xi0, xi1, and xi2 in the range 0 to 1. You use xi0 to decide whether you want to sample the diffuse or the specular component. Then you generate phi in the range 0 to 2 pi by looking at xi2 and multiplying by 2 phi. If specular, this corresponds to the phi with respect to the half vector direction. Now you come to the specular component or the diffuse component for xi1. Theta, if it's diffuse, will just be given as earlier arc cosine of the square root of xi1. If it is specular, you can show that this particular formula for theta half for the half angle is correct, involving alpha, which corresponds to the roughness in the GGX model, square root of xi1 divided by the square root of 1 minus xi1. Remember the coordinate frame rotations, so you need to apply the appropriate coordinate frame rotation corresponding to the surface normal or the surface orientation, in both cases for diffuse or specular. In the specular case, you must also compute the incident direction from the outgoing direction in the half vector. So what you actually end up doing is you end up sampling the half vector. You get theta h and phi h. From that, given the half vector and the outgoing direction, you need to compute the incident direction, such that the incident plus the outgoing gives you that half vector. This can be done easily by rotating h about the normal and then reflecting the outgoing direction about the half vector. Finally, you compute the BRDF divided by the probability distribution function, and if the sample is below the visible hemisphere, then the BRDF is simply set equal to 0.